Hey everybody, welcome to the FY6 classroom. Here the F in physics stands for fun. Today we're talking about springs. Now the thing that makes springs interesting is that you can push on them and pull on them and deform them, but they always go back to their original shape. Now you can stretch these things so much to where they bend and break and then they don't work anymore, but as long as you're kind of reasonable with how much force you apply pushing and pulling, they'll typically go back to right where they started. Now springs come in all different forms, but we usually see them in these metal coils I have here. Basically just a metal coil of wire. And we actually have all sorts of uses for springs, and these two I have right here came off this little motorcycle I had sitting around. This one was used in the back brake to release the back brake, so it kind of boing, springs it back out. This one right here, which is just like absolutely brutal. This is like such a tight spring, I can't even take it apart. This one actually came off the kickstand of the motorcycle. I can kind of get a little bit of a bend there. Yeah, came off the kickstand of a motorcycle, but also over here on this tool right here, I have some springs right in this area. So if you were to compress this tool on these wire cutters, by the way, not sponsored by Klein Tools, the spring pushes it back out. It has like a restoring force. It restores this back to its original state. So you kind of squeeze it together. This is actually kind of a weak spring, which is good because I don't want to be like fighting as hard as I need to squeeze this down. There's also springs inside of this pin right here. If you open it up, there it is. There's a little spring right there. Springs are used in all sorts of devices, like very, very small things like the spring in this pin, but also you could go to very large springs like what's in a car suspension. Those are very large springs. Now, when you apply a force to a spring like this, you're deforming it and changing its shape. But it's an elastic material, which means it will return to its original shape after the force is gone. But like I said, don't think you can just stretch these as much as you want and it'll be fine. They eventually do get to a point where they break, depending on how strong the spring is. Now some springs, like this one right here, will break a lot easier than this one over here. Now a very bitter, angry man back in the 17th century spent a lot of time looking at springs because he probably didn't have Netflix or a girlfriend or anything. This guy's name was Robert Hooke. His most famous contribution to science was what he found out about springs. His second most famous contribution to science was basically talking a lot of smack about Isaac Newton. Anyways, Robert Hooke found out that the relationship between the force you apply to a spring and how much it stretches was a linear relationship. So if you were to make a force versus distance graph, you would get a nice straight line like this. And like I said, these things have a limit. And when you reach that limit, it will start to curve and get this weird looking line right here. But everything before that limit makes a nice straight line showing a linear relationship. Now there's an equation out there that's called Hooke's law. Hooke's law is F equals kx. F is the force that you apply to the spring. X is how far the spring is stretched, and K is the spring constant. Now let's talk about that X for a second. X is not how long the spring is, but how long did you stretch it? Okay, so a spring has like an equilibrium state. Right now this spring is in its equilibrium position. It's not stretching or compressing. This is just where the spring rests naturally. But if I were to apply a force, I have deformed it and I've stretched it just a little bit. So I have changed the distance. So that's what that X is. It's how far did the spring stretch. It's not how long is the spring, which could be confusing, but it's just how far did it get stretched. Now K, which is the spring constant, is really just a number that represents how stiff the spring is. The higher the spring constant, the stiffer the spring. The units for your spring constant are going to be newtons per meter. And you're going to see us work a few problems out with spring constants here in a minute. Now, just as a little side note, sometimes you'll see the equation written as F equals negative kx with that negative sign there. Don't worry about it, not a big deal. On the AP Physics 1 formula sheet, it's actually written as the absolute value of the force of a spring is equal to K times the absolute value of X. Now all this comes from like people who are really particular about their signs, the positives and negatives, and all that kind of thing. Now I do want to say the sign is important. A lot of times the sign is very, very important, don't get me wrong. Anyway, back to Hooke's law. I'm just going to use F equals kx for the equation. And we're going to do a couple practice problems. I'll do some easy ones, and then they're going to get harder and harder as we go. If you want to learn how to do these, pause the video and try them out on your own, and then check and see if you solve them correctly. If you're not confident in doing these on your own, don't worry, just give it a try. We don't judge here in the FY6 classroom. And without further ado, let's do some practice problems here, guys. All right, here we go. One end of a spring is attached to a wall. A 25 Newton pull on the other end causes the spring to stretch by 3 centimeters. What is the spring constant? Okay, so let's just draw a little picture here. Here's my wall. We also know that the spring stretches a distance of 3 centimeters, which we need to convert that to meters, which is 0.03 meters. And the question is asking, what is the spring constant? How stiff is this spring? All right, so let's pull out the Hooke's law equation, F equals kx. And we will plug our numbers into the appropriate spot. So F is 25 newtons. K, we don't know that, so we're going to leave that as the letter K. And X is 0.03. And then we're going to need to solve this in our calculator. All right, so we're going to divide both sides by 0.03. And divide by 0.03. That cancels out over here. We're left with 25 divided by 0.03. Get 833. So K is 833.3 newtons per meter. And typically I'm okay with that answer. I'm fine if a student of mine turns that in. But if we want to be specific about significant figures, we need to look up here and say, okay, there's only 2 sig figs here, 2 sig figs here. So our answer really should only have 2 significant figures. So we'll say 830 newtons per meter. And that would be our answer right there. Awesome. First one, easy. All right, our second question here has 2 parts to it. This one's more of a conceptual question, but good one to learn from. So a spring has an unstretched length of 10 centimeters and it exerts a restoring force F. So it doesn't give us a number, it just says it's F. When stretched to a length of 11 centimeters. For what total stretched length on the spring is its restoring force 3F? So basically, if I were to reword this, a spring is 10 centimeters long on its own, but when you apply a force F to it, it goes out to 11 centimeters. So the first question is, how much is it going to stretch if we triple the force? All right, so let's look at this real quick. So if you think about the equation for Hooke's law, F equals kx, I want to rearrange this equation to where x is the only thing on one side of the equation. Okay, so let's do that real quick. Divide each side by k, and then that cancels out. So I have F over k equals x. All right, so that's a good first step to the equation, or to solving this problem, I should say. Now let's think about it with following what I call the rule of 1. So if I were to plug a 1 in for everything on the left side, what's that going to give me an answer for on the right side? 1, right? Okay, so my force is F, and now I'm going to triple that force, so I'm going to make it 3 times greater. So instead of a 1 for the force, I'm going to plug in a 3 for it. And what's my answer going to be? Well, my answer is going to be 3. And what this tells me is that whatever my answer was originally, if I tripled the force, it's going to triple my answer. So let's look at this. So originally it only stretched 1 centimeter with just the force F, but now it's going to stretch 3 times further, so it's going to stretch 3 centimeters. So it's going to stretch 3 centimeters. So the question here is, for what total stretched length of the spring is its restoring force 3F? So basically, it's a really weird way to ask the question, how long is the spring if you triple the force? Well, it's going to stretch 3 centimeters, so it was at 10 centimeters, and now it's going to add 3 centimeters to it, so the answer is going to be 13 centimeters. So if you triple the force and you're stretching it, it's going to stretch 3 times further. It originally stretched 1 centimeter, now it's going to stretch 3 centimeters. Now for part B, at what compression length is the restoring force 2F? So now we're pushing the spring together. So we can think about this logically, right? So if you apply a force F to it, it's going to move 1 centimeter. If you apply a force 3F to it, it's going to move 3 centimeters. So what do you think is going to happen if you apply a force 2F to it, right? Yeah, probably should figure it out. 2 centimeters. Okay, so it's going to move 2 centimeters. But now we're compressing it. We're not making it longer. We're not stretching it. We're compressing it. And the thing is, this whole law of Hooke's law and how it's a linear relationship, that works with its compressions or with its stretching. So with that said, we know that it's going to compress 2 centimeters in. So, and it started at 10 centimeters, and at what compressed length is the restoring force 2F? So we start off at 10 centimeters, and then we are going to subtract 2 centimeters away from it. So that gives us a length of 8 centimeters. So that's how long the spring is going to be when you compress it with twice as much force as whatever this force was right here. Okay, so this one was more conceptual. We did a little math to figure it out and some logic, but yeah, you gotta just kind of understand the relationship. It's a linear relationship, and if you double the force, you double the distance the spring stretched. Also, if you triple the force, you triple the distance that it is stretched, or we can say compressed as well. All right, cool. All right, let's look at a third one. A spring stretches 5 centimeters when a 0.20 kilogram block is hung from it. If a 70 kilogram block replaces the 0.2 kilogram block, how far does the spring stretch? All right, so let's just go ahead and make a little list of everything we know. We know that the string stretches 0.05 meters. I took that centimeters and just converted it to meters. That's all I did there. We know that there's a mass of 0.20 kilograms, and so that's like our first mass. And then we got a second mass of 70 kilograms, and that 70 kilograms is later going to replace the 0.2 kilogram block. How far does the spring stretch? All right, so let's draw a little diagram here of what's going on. So you got the spring, and it's hanging from the ceiling, and there's a block hanging from it. So there's really like 2 different ways to go about this problem. I'm going to go about it both ways to kind of show you. So first off, let's go ahead and use Hooke's law to figure this out. Now we know that there's a force of gravity pulling down on this block, and the force of gravity in this situation is going to be equal to the force that the spring has on it. Okay, so however hard gravity is pulling down on it, the spring is pulling back with the same amount of force. So we know that the force of gravity is mg, and the force of the spring is kx. And we can plug our numbers in. We're going to go ahead and use everything from the lighter block, and we're going to figure out what the spring constant is, because that's going to be important to figure it out, figure out how far it stretches with the heavier block. So if we figure out the spring constant, we know that the force of gravity is mass times gravity. Our first mass was 0.20. Gravity, we're just going to put the number 10 in there, round it up from 9.8 to 10. We don't know k, that's what we're going to solve for, and our spring constant is 0.05. So let's go ahead and solve for this. 0.2 times 10 is, well, 2, and then you divide that by 0.05, you get 40. So our spring constant in this case is going to be 40 newtons per meter, and we're going to need to use that to figure out how far it's going to stretch. So I can use Hooke's law again, F equals kx, and we know that the force of the 70 kilogram block, so that's going to be mg equals kx, and now we're going to use the 70 kilograms. All right, and we're back. So the mass is 70 kilograms. Gravity, we're going to keep that at 10. K, we found that out just a minute ago, was 40. And X, we're going to figure that out now. Okay, so 70 times 10, well, we know that's 700. So 700 divided by 40, well, that's 17.5. So X ends up being 17.5 meters. So that is how far it's going to stretch. Also, let's look at our sig figs here. We got 2 sig figs, 3 sig figs, 2 sig figs. So our answer can only have the least number of sig figs we have. So our answer, we're going to round that up to 18 meters. Okay, cool. Now, like I said, there's going to be 2 ways to solve this problem. The first way is, go in this route right here. Also, the second way is you can think about it as we got 0.2 kilograms and then you got 70 kilograms. So your force is going to multiply and get a lot larger. Now, how many times larger is this force now? So we could say 70 kilograms divided by 0.2 kilograms. So the force is 350 times larger than what it was before. That means it should stretch 350 times more than what it did. So if we have 350 and we multiply that by 0.05 to represent the 5 centimeters that it was originally stretched, you would get 17.5. You round that up to 18. So you could have done it going the mathematical route like I did here, or you could have done it conceptually and thought of the fact that, hey, how many times larger is the force now? So it should stretch that many times greater. Okay. All right, now we have a 60 kilogram student is standing atop a spring in an elevator that is accelerating upwards at 3 meters per second squared. The spring constant is 2.5 times 10 to the third newtons per meter. By how much is the spring compressed? Okay, so this one's a little bit more tricky. It involves a little bit more stuff, some things that you've probably learned from the past. Okay, so this whole thing is accelerating upwards at 3.0 meters per second squared, and the mass of the student is 60 kilograms, and the spring constant is 2.5 times 10 to the third newtons per meter. And we're trying to figure out how much is the spring compressed, so we're looking for the spring compression. Now, one thing you got to remember about a scale, or whenever you're standing on something like this, is that it is compressed due to the normal force. So however much normal force you have, the spring is going to compress that same, or have that same force applied to it. So you got a normal force going upwards. Whatever your normal force is going to be equal to the force of the spring in this situation. Okay, so I'm going to do a little side work over here, and I'm going to say that the normal force is equal to mass times gravity. And that's true if you are on a surface that is not accelerating upwards or downwards. But if you're accelerating upwards, then you need to add the force from your acceleration. And I could rewrite that as normal force equals m times g plus a, like so, and that works just fine. And now we're going to come back to our main problem over here, and we say that the normal force is equal to the force of the spring. Okay, so I'll rewrite my equation. I'm going to go a little lower because I'm going to start overlapping. My normal force is mg plus a equals, and then the force of the spring is kx. All right, so now I'm going to start plugging in my numbers and solve for how far the spring stretched. This is the easy part right here. So 60, g is 9.8. That should be a plus sign. Pretend that's a plus sign. And then the acceleration is 3 equals k, which is 2.5 times 10 to the third multiplied by x. All right, so here we go. We're going to just go ahead and solve for the left side. There's a few more numbers here that's going on. Remember, do the parentheses first. 9.8 plus 3 equals 12.8. Multiply that by 60 times 60. You get 768. 0.5 times 10 to the third multiplied by x. Now I need to divide both sides by 2.5 times 10 to the third. Divide by 2.5 times 10 to the third. Now if you're using a calculator that's not the iPhone, maybe like a scientific calculator, don't forget to put this in parentheses down here. All right, so what I'm going to do, I know that 2.5 times 10 to the third is the same as 2,500. So I'll do 768 divided by 2,500, and you get 0.3 0.3072. So x equals, and let's see, how many sig figs do we have? We have 2, 2, and only 2 here. So your answer would be 0.31. So 0.31 meters. Right. Now we moved on to a very light ideal spring of spring constant, which also known as force constant. 250 newtons per meter is 0.15 meters long when nothing is attached to it. It is now used to pull horizontally a 12.5 kilogram box on a perfectly smooth horizontal floor. You observe that the box starts from rest and moves 0.96 meters during the first 1.6 seconds of its motion with constant acceleration. How long is the spring during this motion? Well, let's start off with drawing a picture. Here's your box, here's your spring, and there's a force being pulled that way, okay? Now, we know that there is an acceleration of this entire system, and it said it, well, it didn't say it, did it? Well, we know the whole system is accelerating because it started from rest and then it moved, so it had to gain some sort of velocity throughout the whole time. We're probably going to need to find that acceleration. And then let's go down. We know that the spring constant K is 250 newtons per meter. We know that the length of the spring is 15.15 meters long when nothing's attached to it. I'm just going to underline that as important information. I'm not going to put that in my list down here because you might put that as the letter X, and then that gets confusing with all the different X's that might go on here. So I'm just going to underline that. No, hey, I'm going to come back to that later. And then the mass of the box is 12.5 kilograms. It's a perfectly smooth floor, so no friction. You observe that the box starts from rest, initial velocity of 0 meters per second, and it moves a distance, all right, so that's the final position of 0.96 meters, and it does all that in a time of 1.6 seconds. Okay, so like I said, we're first going to need to find the acceleration because the whole premise of this problem is going to be that force applied is going to be equal to the force of the spring. So we need to find how much force is applied. To figure out the force applied, you would say mass times acceleration is going to equal to kx. We don't know this acceleration. We do know the mass, but we don't know the acceleration. So we got this other information here that we can use to find the acceleration. Gotta go back to your kinematics equations, and you'll remember the equation x equals x naught plus v naught t plus 1/2 a t squared. So this is kind of like side work to find the acceleration. So our final position was 0.96, our initial position was 0, our initial velocity was 0, our time 1.6 plus 1/2 a, our time is 1.6 squared. All right, cool. Well, this 0 goes away. 0 times anything is 0, so that part goes away as well. And we're left with 0.96 equals 1/2 a times 1.6 squared. Got 1.6 times 1.6 equals 2.56. Multiply that by 0.5, which is 1/2, 1.28. So you got 0.96 equals 1.28. A, divide both sides by 1.28, divide by 1.28, so 0.96 divided by 1.28. The acceleration is 0.75 meters per second squared. So we gotta use that and plug it in over here. So we got 12.5 times 0.75 equals 250. And then we need to figure out how much it stretches. We got 12.5 times 0.75 times, there we go, 9.375 equals 250 times x. Divide both sides by 250. We're going to get by 250. We get 0.0375. 0.0375. That's how far it stretches in meters. And the question is asking actually how long is the spring, the entire spring. So you're going to have to add it to that 0.15. So we'll do 0.15 plus 0.375 plus 0.15, you get an answer of 0.1875 meters. And like I said, if you were to turn that into I would count that as fine, but if you want significant figures, you got to look up here. We have 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs, 2 sig figs. So you can only have 2 significant figures in your answer. So we would have to say 0.19 meters as your answer. All right, so a 3 kilogram brick rests on a perfectly smooth ramp inclined at 34 degrees above the horizontal. The brick is kept from sliding down the plane by an ideal spring that is aligned with the surface and attached to a wall above the brick. The spring has a spring constant of 120 newtons per meter. By how much does the spring stretch with the brick attached? Now it says it's a perfectly smooth surface, so we're going to ignore friction. And let's think about this. We got mass equals 3.0 kilograms. We got an angle of 34 degrees. We got a spring constant of 120 newtons per meter. And by how much does the spring stretch? So we're looking for X. How much does it stretch? Now I need to get a smaller marker here. Now let's actually zoom in on this picture and get an idea of what's going on here. All right, so you know that there's a force of gravity pulling down on the brick, but the spring is working horizontally, or I shouldn't say horizontally, but in the same direction that the ramp is. All right, so we usually say that the ramp, going up the ramp is the X direction and perpendicular to the ramp is the Y direction. So let's think about this. Let's break this into a right triangle right here. So you got the force of gravity in the Y direction, and we got the force of gravity in the X direction. That's how I like to denote which one of these directions there are. Okay, so you got FGX, which is parallel to the plane, and whatever FGX is, however much force there is pulling it down the ramp, the spring is applying the same amount of force upwards. So with that said, we're going to be able to say that whatever FGX is, it's going to be equal to force on the spring. All right, so how do we figure out what FGX is? Well, if we got FGX equals force of the spring, so let's come over here. We're going to use our SOHCAHTOA, and we're going to figure out, okay, well, this is the angle of the ramp, so that's going to be equal to this angle right here. And this angle is, if we're worried about the FGX, that's opposite of our angle, so that gets rid of cosine. That's not going to be useful to us. And we do know what FG is. We can figure that out actually. So we know the hypotenuse. So that gets rid of TOA here. So we're going to use sine. So we say sine theta equals FG, whatever the opposite is, which was FGX, divided by FG. And we're going to rearrange this equation to where it's FGX. So we could say FG sine theta is equal to FGX. There you go. Now you can plug FG sine theta in up here. So we're going to say FG sine theta is going to be equal to force of the spring. And we know that the force of gravity is mass times gravity. So mg sine theta is equal to the force of the spring. And we'll say mg sine theta is equal to kx. Now we're at a point where we can plug these numbers in. All right, so let's go ahead and say 3 times g, which is 9.8, sine of 34 is equal to k, which is 120. And we don't know what x is. That's actually what we're going to be solving for. So let's go ahead and solve for this in our calculator. If you're using an iPhone like me, you want to turn it over to where it has the bigger menu there. Well, you want to do the sine 34 first, so you do 34 and push sine right here, you get 0.55, la la la. Make sure it's in degrees. If you push radians, it'll say radian right there, but we don't want that. Multiply that by 3, then you multiply that by 9.8, you get 16.44, but we're going to end up dividing both sides by 120. So all of this divided by 120, you get 0.137 meters. And then finally with our sig figs, let's look up here. We got 2 sig figs and 3. So we can only have 2 sig figs in our answer. So we'll say x equals 0.14 meters. All right. Well, guys, that was a lot of fun. I hope you learned a lot about springs and also how to calculate and solve for spring problems. And we'll see you in the next video. Bye. All right, guys, if you like this video, make sure to hit that like button, especially if I solve one of your homework problems for you. Also, if you want more content and need more help in the future, go ahead and hit that subscribe button. See you later.